Welcome to the second part of my video on an introduction on how to learn logic and how to take care of some simple problems that often occur when beginners are trying to formalize certain statements in logic. So let's talk about negation a little bit. Negation can be hard to figure out, not on its own, obviously, but for how it interacts with other statements. And the main issue is that negation flips connectives and quantifiers. So connectives are and or, and quantifiers are universal and existential quantifiers, as we discussed in the last video. So this is, of course, true in the programming languages you're used to. If you're already a programmer working in Java or C++ or Python or some similar language. So if we have a statement like, if not A or B, then do the following, this requires that not A and B is true for the then portion of the statement to be executed. And note that the statement is negated, right? So this statement is true if the subsidiary statement A and B is false. Now, if you have a conjunction, an and, A and B is false if either A or B individually is false, right? If you have false and true, the result of that is false, right? Both A and B have to be true. So if either one is false, then the whole statement is false. Okay, so you can then easily restate this with that in mind. It's the same as, so not A and B is the same as either not A or not B, right? So not A is true when A is false. And you only need one of these two sides to be true, or both, which that would be fine as well. So if if A is false or B is false, then you get a true result. So let's prove it. Now let's use this very simple tool that logicians use called a truth table. A truth table looks like this. So on the left-hand side of this table, we have each of the elements. We have A and B. And we just go through and have all of their possible values. The only values that these propositions can have is true or false, and so there are only four possibilities here with two of these essentially variables. And these are the two values, true and false. And so we can just go and check them all. So if true and true, A and B are both true, then that equals true. And the opposite of that, not A and B, is false. So in the second line, we have true and false. So if either one is false, then the result of an and is false. We flip that around, it becomes true, and so on and so on. So you can see the end result is false, true, true, true. So how does it look if we do the other statement? So we've just done the original statement, not A and B, sort of building it up left to right. Let's try the next statement. The thing that we want to prove is equivalent. So is not A and B the same as not A or not B? So same thing, truth table. We've got two columns, one for A, one for B. We have all the different possibilities. We look at the parts of the statement individually and try to build it up. So not A is just the opposite of A. So instead of true, true, false, 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 we get false, false, true, true. Same thing for B. We got, instead of true, false, we get false, true, false, true. And then if we combine them, looking at the third and fourth column and taking the or of that, it's only false if both of them are false, right? So if either one is true, then the whole thing is true. And so we get false, true, true, true as our result. Well, what do you know? That looks exactly the same as the first statement's truth table. The not A and B has exactly the same outcome for the same inputs for A and B as not A or not B. Since those are the only possibilities, we've now proved that they're equivalent. We get exactly the same result for exactly the same inputs, and that's all there is. So we know now that these two statements are in fact equivalent. Great. So let's look at quantification now and see if we can make kind of a similar determination. So and or flip essentially when you have them negated, right? If you pull the negation from the outside of the statement into the inside, you flip the connective. So the same is true with quantifiers. So if we have the statement not for all x a, where a is some proposition, something that could be either true or false, is it the same as exists x of not a, right? We've pushed the negation into the statement, and we flip the quantifier. And let's try to prove, are these things equivalent? You don't just have to take my word for it. We can prove this logically. And just so it's not so abstract, let's look at a very concrete statement. So it's not true that all men are tall. And we can do a rough paraphrase in English of what the logical opposite of this would be, or pushing the negation inward, flipping the quantifier, and describe it as some man is not tall. Right? So we've taken a not for all and turned it into an exists not. So what does this look like formally? Here we have it on the right. So it's not true that for all x, if x is a man, then x has the attribute of being tall. And if we flip that around, pushing the negation inward, we wind up with there exists x such that x is a man and x is not tall. And hopefully you can see that from the English paraphrase that these two things mean the same thing in English. If it's not true that all men are tall, then there must be some man who is not tall. Right? That gives us the obvious conclusion. However, we've got a little bit of a complication. These two logical statements don't really look alike. We've added this implication here that makes them look different. So my goal here now is to show you how, in fact, incontrovertibly, according to the rules of logic, that these two things are equivalent. It's not so easy to do this with a truth table, so we're going to take the transformation that we proved in the last step, right? That not A and B is the same as not A or not B. We're going to use that rule that we've proved to be true and try to prove that this first statement in logic, not for all, if x is a man, x has the attribute of being tall, is equivalent to there exists x such that x is a man and x is not tall. Right? So the first problem is we've got to get rid of this pesky implication sign, the if operator, if you will. And how do we do that? Well, there's another rule in logic that is kind of similar to the rule about flipping the and or when it's negated. It tells us that if we have an implication, if A implies B, then that's the same as not A or B. And again, you don't have to just take my word for it. We can do a truth table. Great, to tell us that this rule really makes sense and we can use it in a later proof. So again, we go through all the options for A and B. We look at each of the components of the statement to make this very step-by-step, very easy. So the first one we look at is not A, and you can see how column 3 is just the inverse of column 1. Then we look at the implication sign. So what's the truth value? What's for this operator implies? And then we can go to the right side and combine these two things with an or and get the indicated result. So I encourage you to just try to replicate this truth table for yourself. But let me just pause here and are these really the same? Does this truth table work? In fact, we've got one line that if you haven't seen this before, you might question it. Does false really imply true? How does that work? Well, let's look at that for a minute. Now, one explanation that you can have is, well, it's a logical operator. It says whatever the language developer says it means. And this is certainly true in any programming language. You don't really get the option of arguing whether a particular operator in Python or Java is one that you like or not. You can choose to use it or not sometimes, maybe. But the language designer says what it is, and as long as they provide a consistent semantics for how the language works and they can explain it in a way that's not ambiguous and it's not inconsistent, well, then you just accept it and move on, right? That's an operator in the language. But we might pause and say, well, why does this make sense? Why is this element of logic a reasonable way to model thought or the way the world works? So let me just give you an intuition. So, if this intuition doesn't work for you, then go back to this first justification. It is what it is. That's how it's defined in the language of logic. And this is consistent across, many, many different classical logics. So it's not just some invention of mine. But let's try to look at this intuition. So why does false imply true? Well, you can think of it as, suppose I tell you that the moon is made of green cheese. It's something that's obviously false. And from that, maybe you can conclude pigs fly. Okay, false implies false. You've got something that's false. Well, okay, you can imply you've got something that's silly. You can conclude something else that's silly. But something that's might be a little strange is, can you conclude something that's true? Well, one way to think of it is, if you believe that the moon is made of green cheese, you'll believe anything, and whether it's true or not actually doesn't matter, right? So I hope that works for you as an intuition. Certainly logicians and philosophers have argued over this particular line for thousands of years, but we've still got it because it actually works in the mathematical system of logic. In the same way, you might not think that some element of the calculus actually works for you. This notion of we always get this notion of successive approximation when we're learning calculus as seniors in high school or maybe freshmen in college, and whether that intuition works for you or not, the math works, right? And it's been well proven. So that's the situation we have here. Hopefully the intuition works for you as well. All right, so that was a brief digression back to our regularly scheduled derivation here. So we've got this intuition, back to the math. All right, so here we are. We're trying to prove that this first logical statement equals the second one, and our first problem is to get rid of the implication. And so here's what the implication means. We want to turn this A implies B into not A or B. So let's call this first thing that we're given step one, and we're trying to prove this second existentially quantified statement using these two tools, these two transformations we've just had. The first is flipping connectives, and the second is eliminating implication. So let's try to get from step one to the conclusion. So here we have a step two. So this is the transformation of removing the implication. So we've just proved with the truth table that this is a valid rule, that we can replace A implies B with not A or B. So if we can go from step one to step two doing exactly that. So the instance X man becomes not instance X man. The second part of the rule, attribute X tall, remains unchanged. And instead of an implication, we have an or sign. So hopefully you can see how we can get from 1 to 2 with the rule, the transformation rule just below it. Similarly, for our next step, then we're going to flip the quantifier because of the negation. So note the two red boxes here are showing what's happening. We're taking this negation from the outside of the expression, where we have not for all something or other, and turning it into exists not something or other. So we're moving the negation inward, flipping the quantifier. For our next step, then we're going to flip the connective. And in step 3, we've got the pattern not or two things. And we're going to turn it into exists not one thing, not the other thing. Okay, so hopefully you can see that the not or in green turns into an and then this first part of the disjunction, this first part of the or statement in red, not instance man, turns into not instance man. And the second literal in the disjunction, the or statement, attribute X tall, turns into not attribute X tall. Okay, so hopefully you can see how we go from step 3 to step 4. And again, it's because not A and B is the same as not A or not B. So here we've got the thing in red is the A part, and the thing in blue is the B part. So we're turning not or into an and, not. And then finally, so we're left with this not. We can get rid of that. We can simplify. So double negation cancels out. And then from step 4 to step 5, we've got, hey, what do you know? It looks exactly the same as the thing we were trying to prove syntactically. So this is the magic of logical proofs. Hopefully all of you have had some exposure to this just in high school geometry, when you maybe proved one triangle was equal to another triangle by using things like the side angle side rule. So we've just had a grab bag, or a toolbox, if you will, of transformation rules that are very simple, that we've proved with truth tables individually. We know they're logically valid, and we're moving gradually from the things that were given to be true towards the thing that we want to prove by applying these incontrovertibly correct steps in sequence. That's the magic of a proof. So you take these little simple mechanical steps and you transform the things that you know to the thing that you're trying to prove is true. And if you've done that, and if the rules you've applied are logically valid, then you've got a logically valid proof. You've shown incontrovertibly that it's true. And so just as in geometry, you might want to be happy and put in a statement QED, quod erat demonstrandum, which in Latin means that which was to be demonstrated. You've proved that they're the same. Yes, indeed. Great. So, great. We've had kind of a long diversion into proving that some of these transformations are true. Now you've got a toolbox you can use that helps you determine why the things that you're writing are true or equivalent or not. These are important things that you need to know if you're going to be writing logic. You've got to have these basic mechanical transformations under your belt, as it were. So back to, why do we learn this? Because this takes some time to learn. So the thing that I assert is just having some labels for your columns. If you're creating a database or a JSON or an XML schema, it's just not enough, right? So if the terms that you create, the names that you give things, undoubtedly will seem very clear and unambiguous to you, but they're never really clear for the next person, right? And we've all had this experience as programmers. You write something, either it's code or a database or some kind of schema, and then you hand it off to somebody else, and that person comes over to you. Hopefully you're working in the same office, or they give you a call and they say, well, what did you mean by this? What are the boundary conditions? What are the constraints on the field? How is this related to other things? The things that you thought you were clear just by giving it a name, and could be even an abbreviated name, are never as clear as you think they are, because your context, your knowledge, your assumptions are always going to be different. And so this is why we have data dictionaries and data warehouses that are designed to give us a way to record what we meant when we created a table in a database or a variable in a program or what have you. Without a clear explanation of intended meaning, the next programmer is really likely to use your data in a different and slightly wrong way, and that's one of the ways in which we get bugs in our code. Especially in enterprise-level software, where you have lots and lots of tables. And then the thing that I'll say that's maybe a little bit more controversial, or at least less typical, is that having these comments, even if you do comments, all right? And so the fact is, we all know that most people don't like to write comments. Most people don't like to document their databases, their schema, their code. Very rarely do you actually have good comments. But even if you have good comments, if you have thousands of these fields, and that's what we have nowadays in enterprise software or big data repositories, there's no way for a single human or even a collection of humans to keep all of these definitions or intended meanings in our head. We need some automation that can be applied to keep them consistent. And if all you've got are English definitions or some other natural language, that's just not enough. That's not an automatable system that a machine can tell you whether your definitions are right or consistent or not. Right. So hopefully you're on board with that justification of why we need to spend time to do this. What did we learn in this, in both part 1 and part 2? Some tips on how to write logic, some pitfalls to avoid, and some tools in your toolbox that can help you prove manually why one simple expression is the same as another or not the same. And ideally, after you've got these things so that they're so intuitive that you're not having to write proofs of these simple things, then let the machine do the really heavy lifting if you've got thousands and thousands of these definitions. Right. So if you found this informative, please like, subscribe, and comment. Check out the other resources. I've got lots of other videos showing more advanced stuff. This was a fairly step-by-step introduction to some issues in logic. If you want to put all this together, watch some of the other videos. And then we've got software that is all open source that you can apply to actually use this stuff in practice. And I've also got a transcript of this part 1, part 2 video as paraphrasing logic, and I'll put a link in the comments. Right. Thanks very much.